extremely important. Everything you are going to do in cybersecurity, you can capture it in one word, which is risk assessment and risk mitigation. So within which we are looking at security life cycle model. I'm going to introduce a concept. Sort of it captures multiple things we should do in this situation. Then I will discuss some process that are there. This is developed by DOE, Department of Energy, for risk assessment. Then I will kind of distinguish what is qualitative risk assessment versus quantitative risk assessment. Then I will talk about some risk mitigation strategies. That's how we'll go. So as I articulated in my previous presentation or the previous module, we need to go beyond IT security, right? Because there are attacks of type, different nature, through spear phishing or through denial of service or other means, or coordinated cyber attacks, multiple elements being compromised. One can still get into the system even if we have a secure IT infrastructure. So as I said, the reason being we have a legacy infrastructure, limited encryption capability. Some of the devices may not be able to even do encryption. Their computational capabilities very limited. Poor patch management. There could be bugs in the software, and security was not built in those things in the legacy infrastructure. That is inherent challenge. The encrypted communication itself, as I was telling before, could be subject to attack like replay attack, denial of service attack, timing attack, just to perturb the timing between packets. That can create malfunction depending upon critical application. If some critical application operates in milliseconds, like protection kind of application, you kind of play with the timing, then the whole thing can be impacted in a negative way. Advanced persistent threat, like a state actor performing reconnaissance and taking their time to plan and execute, those are typically coordinated attack. Multiple things are compromised, like the example Ukrainian attack. It is an example for APT. Then when it comes to the cyber threat landscape, as I said, it's evolving and it's dynamic. And that is the reason we need to kind of go beyond the IT security, have a defense in depth kind of notion of security. I think that's important. I think this slide is a very important slide. You can see a reference at the bottom. There is a paper published in Proceedings of the IEEE, which is kind of a not a journal type paper, neither a survey paper. It's somewhere in between, semi-journal type paper. A lot of concepts are discussed there from a perspective of wide area monitoring, protection, and control. Essentially, the securing the bulk power system. What are the challenges there from a EMS, energy management system application perspective? So what it provides, I think the idea is we would like to deter the attacks. Let's start with the attack, the cybersecurity life cycle model. How do you deter the attacks? Okay, make sure that you don't have a whole lot of enemies. I think that's a good thing to have. The attack deterrence, that is one way to do it. The other way to do it, between nation states, there may be a what you call international agreement in place through UN and other means, actually, United Nations, no first use policy or whatever it is. So they all comply with, in that case, you can deter. Deterrence can come into play. But when you are dealing with the cyber world, it's not just nation state. There are terrorist group, hostile, other kind of hackers, and people want to make fame, gain fame and make money and so on. So you can't necessarily have legislation or international laws to prevent them. So deterrence has some value, but not solve all the problem. So some attacks, many attacks go beyond deterrence. In fact, there are not many laws in place, international laws in place, except bilateral agreement may be in place, but not as a global agreement yet to be in place. So what you see is attacks do happen. Then how do you prevent those attacks happening? The prevention, essentially, you have this risk assessment. Okay, have a systematic process analyzing what are your risks. If there are high risk situation that is there, how do you mitigate those risks? I think that is very important. There are a lot of mathematical tools people use for risk assessment. So we will be discussing qualitative and quantitative risk assessment. I think that is important. So the way I listed this diagram, it's a sort of wheel with spokes. You see in the middle, you want to have a cyber physical security of the grid, which is a holistic thing, for which you want to have prevention, detection, mitigation, resiliency, attribution. All those things are spokes of that particular wheel. So not every attack is preventable, even if we have like good firewall, risk assessment, all the things. As I said, the threat landscape is changing. New vulnerabilities getting discovered. There are zero-day exploits. That means there is vulnerability for which no patch yet to be known. So those things, will result in attack actually being successful. They were not necessarily prevented. Then you need to have a capability to detect. This is an online thing. Detect ongoing attack. That is where the information or intrusion detection, anomaly detection, all those concepts we talked about, that come into play. Of course, there are different flavors of anomaly detection, leveraging the physical properties of the system and so on. There are a lot of model-based anomaly detection, those kind of algorithms people do, beyond the conventional IT anomaly detection. Once you detect there is an attack, then there has to be a way to mitigate those attacks. Online mitigation in place. Either you do those mitigation in the cyber layer or in the physical system layer or both layers. Truly speaking, it has to be in both the layers. So the mitigations, they are in both levels, it could happen. Then you have the notion of resilience. So mitigation is fine. You have to keep the grid operational with the critical functions, critical loads being served, not letting a fault, attack cascade into a blackout and things like that. The resilience is much more richer concept than just doing little mitigation and here and there to keep the system remain operational, to contain the fault, to prevent blackout. Those things come into picture. That's where there is a notion of attack resilience. So you have fault resilience. We are all familiar with N-1 contingency. So one unit is down, whether a line or a generator or bus, whatever it is, still the North American grid is reliable. That means it is N-1 contingent or N-1 redundancy, they call it. But if there are more than one element is down or compromised, there is no guarantee that the system will be stable and reliable. It may be some cases, but there is no guarantee for all cases it will be reliable. When we think about cyber attack, it is not that randomly they are going to create one line outage, one generator being taken down. No, they are going to create a coordinated attack in which multiple elements will be targeted. Like in the Ukrainian attack, 30 different substations were targeted and the breakers in those substations were opened to create a regional blackout. So in those cases, whenever we think about the conventional N-1 contingency analysis, that falls short when we think about cyber security resilience. So we need to go beyond N-1 contingency analysis. So there is a lot of attempt to do N-K contingency analysis, even for extreme events like hurricane and other kind of weather conditions. But those are all kind of predictable. Even N-K, it is going to come in the same vicinity. Whereas from an attacker perspective, it could be from anywhere. So thinking holistically, not just providing redundancy. Redundancy is one way of addressing that issue. But redundancy for how long? Even if you say K equal to 5 or 10, there is no way you can provide resiliency. That's where the notion of attack resiliency, how do you design your control algorithm that is resilient to attack? that is more powerful than throwing more hardware, more resources in a redundant form. So those kind of research is coming to attack resiliency. We do a lot of work there. So then the attack attribution. So something has happened. How do you attribute where the attack came from, so that those whoever caused those attack, they are accountable, right? Or even attribution could be used as a deterrence. If you have some attribution capability, you say, hey, if somebody is going to target me, I can detect where the attack came from. Then the adversary will hesitate even doing attack. For example, in front of your home, if you say, my home is AAA certified or AAA secure system, the burglar will think twice even before coming. So something like that. So attribution is a powerful technology concept and technology that can be used to deter attacks. But the problem there is building attribution system is very hard. So forensics, people do forensics, attack forensics. This happened, where it came from, so that we learn from it, so we can prevent similar things happening in the future, and possibly make the attacker accountable, hold responsible. So this is the wheel where you want to deter, everything is not deterrable, prevent, everything is not preventable, then the ability to detect online. The moment you detect, then you have mitigation either in the cyber or physical, immediate reaction. The resiliency is a long-term notion. Then you have the capability for attack attribution. Each one feeds itself, within which if you see inside that circle, there are a lot of engineering and what you call research challenges. One can use all complex techniques, machine learning techniques to learn the behavior, to predict the future behavior. That could be part of anomaly detection. Game theory kind of mathematical tool to model adversarial behavior as part of attack defense exercise. Those are examples. And of course, one can use test beds and other kind of concepts to validate different technology solutions. So those are all nicely captured. If you are interested, you can look at the paper listed at the bottom. The overarching goal is to transform the fault resilient grid of today into an attack resilient grid of the future. Fault resiliency to attack resiliency is not just straightforward, because the attacker decides where to attack and when to attack, how many elements are going to be part of the attack vector. Those are all under the attacker control, compared to in a fault situation where we can kind of estimate and predict where the fault based on aging and other thing. There are well-established models that exist. The other important thing is, we see in the box on the left, it is not just a technology solution. Coming back to the question earlier we had, who is responsible for doing it? There are processes in place. There are regulatory framework in place, like CIP compliance in place. There are technology vendors, they have to do their job. And of course, there are people who are operating the system, they have to be well trained. So it is basically a responsibility of everyone. Technology, process, people, and regulatory as a synergistic way, they address the holistic security solution. So it's not just a technology alone. In that context, education and workforce training is important, and collaboration between university, industry, government, in several forms. It is very, very essential in that context. So this is the other chart just to illustrate what is defense in depth. I kind of mentioned one could have infrastructure layer security like a firewall, intrusion detection. Then you go into the application layer. Each one of those applications in the energy management system, state estimation, or AGC, or contingency analysis, all critical applications, they can be secured. Whatever data they rely on, they can be validated through an anomaly detection. Whatever decision they make, there are some techniques there that are there. For example, one is called moving target. Moving target means when the measurements are coming from the field, I have some suspicion about some measurements because they may be compromised, but you take redundant measurements more than what is needed. For example, in the state estimation case, only take a subset of them. Which subset you are going to choose at a given point in time? Only it is done in a randomized manner so that the adversary doesn't have a clue which measurement is going to use for the state estimation or any other application. So try to confuse the adversary by doing randomization in estimating the state or using the measurement or doing the control. Those kind of techniques can be employed at the control center EMS application in addition to the anomaly detection, validating the data that is coming in, or bad data detection methods. In state estimation, bad data detection is there for conventional bad data, but what about false data injection? Somebody is injecting false data, that needs to be detected as well. So a lot of research is going on in the university and also the Department of Energy, national labs, some industries too, on how do you secure the control center and the EMS, those applications, along with other elements, even in the substation and so on. Anomaly detection is one. Attack resilient control algorithm is the other one. Then using techniques related to moving target and other things, randomization is other kind of techniques commonly used. So the point here is not just to start stopping there at the firewall and intrusion detection system. We can do security features within the energy management application. Think about this control center is not a transmission control center, it is a substation control center, the distribution control center. Then this whole application will be slightly different. It is distribution management system. Whatever the application, whether it's related to routing the power flow or outage management or contingency management, those things have to be secure as well. The other concept beyond the defense in depth and the end-to-end life cycle I talked about before, this is about we need to protect the generation to actual consumption. The whole end-to-end delivery of the energy infrastructure needs to be secure, actually. Otherwise, what happens, most of the emphasis has been on the bulk power system, that is protected. The distribution grid, okay, if somebody compromises, it doesn't really have any impact on the bulk power system, which is no more true, actually. Ukrainian example, 2015 is a classical example. Most of those targets were distribution substations. By compromising multiple distribution substations, one can create an impact on the bulk power system as well. So that's why we need to make sure that every element in the end-to-end delivery has to be secure, maybe varying level of security, but security is end-to-end as opposed to just saying, oh, only bulk power system is secure, but distribution system we don't secure, or AMI we don't secure. So this is just to illustrate the Department of Energy. This is what the kind of chart they have. On the right, you see generation, bulk generation, transmission, then the substation, then the feeders automation level, then the home level. Everywhere, automation and communication and the cyber elements are there. Security of different flavors can be embedded in each one of them. As part of their funding portfolio, they track which project addresses security at what layers and what aspect of the system in this end-to-end chain. So far I just introduced three concepts. One is the life cycle model from a prevention, deterrence all the way to attribution. The other one is defense in depth. The third is end-to-end span of the delivery system. Security has to be there. Let me move on to the risk assessment itself. So the risk assessment, as I said, if you go back to that wheel diagram, risk assessment is part of the prevention strategy. It is typically done offline. You do a risk assessment study, make sure that your system addresses all high-risk scenarios, and also you could have online capability to detect malicious behavior that can be fed into the risk analysis engine. So before getting to the risk assessment itself, it's important to distinguish. In the very first slide I mentioned, modern power grid or smart grid is a cyber physical system. I'm going to introduce one more layer. It is a cyber control and physical system. Okay, there is a control layer between cyber and physical. So you see on the left, what you see is the system and networks, like servers, those are part of the cyber elements, the devices and so on. Somebody is creating an attack of whatever it is, phishing, malware, spoofing, or man in the middle, or whatever attack that is on the network or on the devices or the servers, that is cyber layer is compromised. That doesn't mean that there is going to be a blackout or equipment damage or something going to happen. No, they need to play with the control system. The control system could be related to generation function or transmission function or distribution function. Those elements have to be manipulated. So whereas if you look at cyber layer, a sophisticated IT security person may be able to hack the cyber layer, but they may not necessarily know what to do. Okay, I have a control over this particular system. What am I supposed to do? They need to have understanding about the control application so that they can turn on or flip the right switch so that it has impact on the physical system in terms of stability or blackout or economics, whatever that may be. So that is where, as I mentioned, the cyber layer has to be protected from the network side, from the server host side. The control layer also has to be protected. So there are multiple layers that can be protected to have the defense in depth. So coming to risk assessment, what is risk? Risk, as we know in the traditional sense, probability of some event happening multiplied by the consequence of that event. Like, for example, extreme events. What is the probability of a hurricane happening in some region of the United States? They have probability. They can compute the probability based on weather model and historical data and so on. If an event of that kind happens, what would be the consequence? If a hurricane of this level, this category 2, 3, whatever it is, then it will knock out this many power lines. Then the consequence can be computed. Then you multiply those two things, you have a risk index. So then you kind of enumerate different risks there. That's how risk assessment is done. It is a very well established field. When it comes to naturally occurring events, there are models that exist. They can predict, they can accurately compute risk indices. The problems with the cyber risk assessment is it is a probability times consequence. Let us look at the probability itself. The probability itself has two components. A threat source exploiting a vulnerability in the cyber layer. What is the probability? The joint probability. The joint probability, the probability that a threat source like a hacker group or a hostile nation exploiting a vulnerability in the substation automation system or something else, or going through a pathway into the network, starting with the access point, going into the system from step by step, what is the probability exploiting those vulnerabilities? That combined joint probability, that is what needs to be computed. Once that probability is known, then we can say, oh, they tripped these lines or they opened this number of breakers, then we can compute what would be the consequence. Just like a traditional impact analysis, contingency analysis, you create those contingencies and study, run simulation or things of that nature, you can compute what would be the consequences. When you multiply those two things, you have index. But the problem is, how do you compute the joint probability? Yes, vulnerability assessment is very much possible because you know this particular device has this vulnerability, what is the likelihood that it can be impacted. But when it comes to threat source, who are your adversaries? When those adversaries are going to target your systems, those are all very hard to model mathematically. So threat assessment is more of an art than a science. Vulnerability assessment is a science or scientific or engineering process. Impact characterization is a engineering or scientific process. So without having a threat assessment in a scientific way, it is very, very hard to compute risk indices for cyber threat perspective or cyber attack perspective. So that makes it very hard. So you have a process I'm going to describe, probability times consequence. In this case, it's a joint probability. Sometimes it's hard to compute, so they are subjective. So you compute risk based on the impact and the joint probability. When you multiply those two things, you get a risk. If the risk is acceptable, then you don't need to deal with. If the risk is unacceptable, then you need to upgrade your system security so that the risk is mitigated or the risk is brought under the acceptable level of threshold. So you have a threshold. Any risk scenarios above the threshold, they all have to be mitigated. Those mitigation can come from upgrading your infrastructure, upgrading your application. It is again cost-benefit decision. So which will give the least cost and maximum benefit in risk reduction. So they go through the cost-benefit analysis to reduce the risk. That is the overall framework. From a process perspective, this is from DOE Risk Management Guide. They list this as a 4-step process. One is risk planning, then risk assessment, risk handling, risk monitoring. Risk planning means what is the scope of the system, how often you are going to perform this risk assessment process, those kind of things. Similar to project plan kind of thing, you have a risk plan and who is going to do it, what are the metrics, what are the deliverables, and who is going to be responsible, where the resources are going to come to address any high-risk scenarios, those kind of things. That is the risk planning. Then you actually do the risk assessment. That is a scientific process as much as possible. What are the different scenarios that can exist? Risk scenario 1, scenario 2. You enumerate all possible scenarios for your infrastructure. You have to define the boundaries, the scope of the system that undergoes the risk assessment. So then you kind of compute the risk indices. We are going to talk about it. There are two ways to do it. One is a qualitative way, otherwise quantitative way. So the outcome of this risk assessment will result in risk indices or risk prioritization for all the scenarios in the system. Then you set a threshold. Anything below the threshold, don't care. Okay, these are low risk. Somebody is going to probe your system. Yeah, highly likely, but there is no consequence. Impact is very little. When you multiply those two things, low risk, don't care. There is a targeted user or adversary going to target our system. That consequence will be high. Then maybe its risk is above the acceptable threshold. How are you going to deal with that situation? So you kind of have a threshold, again, based on companies' strategic thinking, what the threshold value. Anything above the threshold, all those risks have to be handled. Risk handling is about bringing down those high-risk scenarios to low risk by security investment, upgrading technologies, training employees, complying with the process, and whole range of things what I talked about before, risk handling. Then the last one is risk monitoring. Okay, you went through this process. We address all high-risk events. Every scenario is below the threshold, acceptable threshold. So we are risk-free. That's great. But tomorrow situation may change. New vulnerability may be discovered. New adversary may emerge. So it is a dynamic environment because the threat itself dynamic, the threat landscape is evolving. So that will cause more the risk to be different than what was computed before. The situation has changed. So risk monitoring has to be done periodically. It has to be updated. So it is a feedback loop. That's what you see here. So this is a 4-step process: risk planning, risk assessment, and handle the risk, and continuously monitor the compliance of those risk assessments still in hold. If not, redo the risk assessment if there is anything changed. So that is a feedback-based loop. It is kind of resource intense in terms of you need to have experts, you need to have some tools, you need to have real data to make these models useful. So let us introduce a few more concepts. Risk assessment itself, it's not just the field engineer, it's your job to do the risk assessment. No, they are responsible. That is the tier 3. The industrial control system engineers, the IT engineers who are dealing with the technologies, they are responsible. But equally important, the business managers, the departmental level, do we have proper training program in place? Do we have enough investment for upgrading the infrastructure and things like that? There are at a higher level, they need to deal with business related processes and investment risk and so on. Then even at the top level, at the board level, risk assessment, what is the strategy? If something were to happen, how are we going to deal with that situation? What is the compliance process in place? How are we going to address ourselves or equip ourselves to meet the changing compliance requirements, changing threat landscape? So they look at more strategically at the top level, the board level, tier level. As you go down from top to bottom in this pyramid, then strategic to tactical level, that's what happens. So it is a two-way information flow. Whatever happening in the field, that information has to be fed to the up in the hierarchy. Similarly, whatever decisions and investment strategies that made, they are sent top to bottom in the information flow. So it is organizational, as a hierarchical thing. Everyone has a role to play, rather than saying the engineers or whoever in the bottom in the hierarchy is responsible. So again, this is given what is the kind of a tier 1 function, tier 2 function, tier 3 function with respect to risk monitoring, risk response, risk assessment, and risk framing. In the interest of time, I'm not going to read each one of them. For example, what tier 1 does with respect to risk assessment determines risk to an operations organization, where the actual risk comes. So then tier 2 may say, develop a prioritized list of mission and business process risk. Then the third is actually conducting the risk assessment itself using tools, appropriate methodologies, and producing that report. That report will be used as part of the decision making by tier 2. That output of the decision will be communicated to tier 1. So the information flows in both ways. I think this is important. So one can look at, it's a process. There is no strict way of doing only this way, not the other way, but it kind of gives you a good idea about what are the things that can go in as part of this process and who is responsible for what and how the information flows between different entities. So let me go and talk about the middle part, or the second step, risk assessment itself, a little more in detail. Risk assessment can be done qualitatively or quantitatively. Each has its own strengths and weaknesses. As I said before, what is risk? Risk is basically probability times the consequence. So we can rate those risks into low risk, moderate risk, high risk. That is one way to do it, as opposed to computing specific index like a number. Instead, we can say low, medium, high. It's more a qualitative definition of saying the risk as opposed to specific quantitative number. So think about one way to do it. So the risk, as I said, the threat, vulnerability, and consequence. So let us say you have a power system with so many buses here, 30 buses or whatever. The generator 1, there is a generator 5. Every substation, every bus has a substation, let us say. The substation is an IT element. It is connected to the control center. It is exposed to attack if it is not properly protected. The cyber, what is the probability of that cyber layer associated with generator 1 and generating station 2, that can be computed through some other means. Once the SCADA topology and what kind of security features are implemented in that network, if that information is given, one can do some analysis to find out what is that probability. Then you go and create those contingencies. Let's say the adversary got into this generating station, they may isolate that generator or cause damage to the generator. Essentially, it is not generating. That's all to the rest of the network. So generator 1 and generator 5, they are taken down. What would be the consequence to the overall system operation? So that can be computed. Essentially, you have a coordinated attack group, 2 generators compromised. It's like a N-2 contingencies, 2 contingencies at a time. Or 1 generator, 1 transmission line, or 2 transmission line. You go and list out all possible, enumerate all possible combination of those things. Then you find out through power flow or other means to find out what would be the consequence. In this case, load shedding. This much load has to be shed. If you take down 2 generators, this blue thing, 163 megawatt of load has to be shed. On the other hand, if you take down those 2 red transmission lines, 363 megawatt of load has to be shed. Of course, what is the probability of each event happening? That is computed independently based on the cyber layer analysis. You have a cyber layer, what technologies are in place, you can compute the probability, then you have the consequence, you multiply those 2, you get the risk index. But as I said, the probability calculation has problem because you embed threat into it. Oh, there is an adversary going to target, but if the adversary doesn't go into target, then the probabilities are wrong. So the probability calculation is subjective, whereas impact characterization is accurate. So there are a lot of research that is going on. How do we make this probability calculation more pragmatic? It is still useful. So one thing, as I mentioned, why that N-1 or N-K contingency analysis won't work, because when it comes to cyber attack, the attacker has the control over space, where to attack. Also, where when they say which unit, whether generator or transmission line or how many such units they are planning to attack, they have a control. Same way, they also have a control on when to attack, whether to attack those 2 generators at the same time or one after other or in some kind of staggered in time. If a stealthy adversary, sophisticated adversary, they know how the grid operates, if they understand the dynamics of the grid operation, they can strategically coordinate those attack events both in space and time so as to maximize the consequence. So those are all very interesting areas of research. Lot of researchers, many researchers have worked on it, including us. There are models and tools available, not necessarily used in practice because the probability calculation is still subjective. The industry doesn't really adopt them fully, but they have utility to compute those indices. But coming to a little more practical, that is useful from an industrial perspective, is the qualitative risk assessment. Qualitative risk assessment, as I said, it is just a coarse-grained categorization of low, medium, high. So that is how we are going to define the risk. For risk calculation, you need this probability of something happen and consequence, those 2 quantities. The consequence of some substation being compromised, let's say there is a substation. Oh, this is a very simple substation, not many high voltage buses are connected, then probably it is marginal. There may be other critical substation which is very critical to the connectivity of the network itself. If that is compromised, then the consequence could be catastrophic. So you give a sort of a sheet of chart like this, in which you don't fill out anything, the one green, yellow and red, don't fill out. Give this thing, you give a topology to them, you give this table, rank or enumerate what are the risks that are possible or scenarios that are possible, attack scenarios. list them as scenario 1, scenario 2, scenario 3, S1, S2, S3 like this. Then place that scenario in this whatever this matrix like table, which doesn't have any entry, let us assume. So they will say, okay, this event is likely to fall here. Let's say this scenario is very high probable, like probing a network, very high probable, but it has negligible impact on system operation. So that scenario is listed here. Some other scenario may be listed here. Some other scenario may be listed here. So the expert will come up with a table like this, enumerating scenario and placing those scenarios in one of those cells. Then you look at that thing. Are there any scenario falls into the red zone? Red zone is the high risk scenario above your threshold. You kind of define the zone red, orange or green based on what is your acceptable level of risk threshold. You define that. Then the risk handling comes into picture. If any scenario is falling into that particular red scenario or red zone, those things have to be mitigated. Risk handling has to happen. For example, in this case, you have S4, scenario S4, whatever that may be. It has high probable and impact is critical, so it falls here. So risk handling essentially says, can we bring this S4 down to the medium level or even all the way below down to low risk? If you want to bring down in the y-axis, essentially what we are doing is we are reducing the probability. Reducing the probabilities, we may add defense in depth or additional layers of security so that the probability is going down. That is possible. Or we could move it in the x-axis. From here, okay, I move here, making this impact critical to marginal or even negligible. How do I do that? There may be additional capacity available or additional lines, redundancy in the physical system may be available. We could potentially utilize them to mitigate those risks. Those are possible. So essentially moving in the y-axis refers to investment in the cyber layer. Moving in the x-axis refers to investing in the physical layer to reduce the consequence. Obviously, the cyber layer investment is much cheaper than physical layer investment. But if you have surplus capacity somewhere or redundant lines somewhere, one could leverage them as part of the risk assessment mitigation process. It doesn't mean that you need to only do either cyber or physical mitigation. One could have a combination of those things also. So essentially, the cost-benefit analysis from a risk mitigation perspective can be formulated as an optimization problem. People have worked on those kind of things also. The challenge with this one is quite intuitive. If you give it to experts, domain experts, they can fill in this chart, which could be used for operational decision making for risk mitigation purpose. But the problem is the same topology, you give it to two different experts and ask them, they will come up with the two different type of results. It is quite subjective. So that's where some kind of correlation among different experts that has to come, and there has to be some kind of convergence and consensus to arrive at what is the final risk matrix from a qualitative sense, and which one of them we are going to do the mitigation. I think that is a very methodical industrial practice. Of course, the quantitative risk, as I said, there are indices computing the probability and consequence. You can kind of compute those indices. As I also talked about, you can do some kind of mathematical modeling for analyzing cyber layer security, essentially the probability of the cyber vulnerability being exploited. There are some models like attack trees, very simple model. There are stochastic Petri net or stochastic Markov kind of models that exist to compute those probability. Then on the right side, you have the consequence analysis for different attack templates. The attack templates are essentially different scenarios. Then you have the probability pi, the consequence mu, then when you multiply those two, you have risk. then you try to mitigate those risks by investing in cyber layer or physical layer or combination. That's how the risk mitigation is done in a quantitative sense. So there are different coordinated attack scenarios that are possible. I kind of mentioned them before. Once you have these probabilities, you can compute risk indices, something like this. So generator 1 and generator 5 simultaneously being compromised. What is the probability? That is that pi, that is 0.03. Let's say there was some analysis using some Markov type of analysis. That's what it came up with. If those two generators are taken down, what would be the consequence? 163, the probability was 0.0003 is the joint probability, both generator going down. Then you have the consequence, 163 megawatt of load is unserved because losing those two generators. When you multiply that probability and this impact, then you get the risk index, something like this. Of course, this risk index has to be normalized so that one can make a consistent decision in terms of indices. It is important. It is not exactly the number matter. Sometimes relative ordering among different scenarios is equally important. This is high risk scenario compared to something else. Whether it is high risk to the extent of exceeding the threshold or not, that is a different decision to make. But a lot of this quantitative analysis still useful, even if you don't believe those numbers, but they can be used to prioritize, triage, what is the relative ordering among those different scenarios in terms of risk. I think that is still valuable tool. So what are the risk mitigation? Is a whole gamut of things that can be done. As I said, you do security investment analysis, upgrade your IT infrastructure, defense in depth, all kinds of things, end-to-end security, all those architectural concepts, what I described, they are all part of the solution, including training and so on. But let us look at some process. Again, there is a concept called mission-oriented risk and design analysis. The essence here is you don't chase every possible scenarios, every possible risk. You have to be strategic. You have to be pragmatic. That's where the threshold come into play. Not every probe, every noise you have to respond to. Then you waste your resources, you deplete your energy and so on. Instead, you kind of be more mission-oriented or more pragmatic. That's what it says. If we look at here, the chart on the right side, what is your system? Which system you want to protect? What is the scope of the system you want to protect? That has to be very well defined. Then who are your adversaries? You can't just chase every possible adversary. That's not the point. It does change, but who are your adversary? That has to be precisely defined. Then what are the missions? What is your mission? What is the attacker objective? Still, they are all subjective things. There could be mathematical models to describe those things precisely. One way to represent attack tree, it is a kind of simplistic tool, semi-mathematical model, it's a tree kind of structure. Hey, this is the way one can enter, then they can go to the next level to next level, then they can go to the root of the tree. Root of the tree is actually compromising the mission. So you can define a attack tree for each of those mission and various entry point to stepping stone to leading to compromising the event. So you can define as the attack tree. If we know some probability, what is the probability somebody can enter into the system, exploit the system entry point, then you can kind of compute what is the path probability. So it kind of gives you some semi-static or mathematical analysis. Then you compute those scores and you determine whether it is above the threshold or below the threshold. Then you do the investment analysis by improving your architecture or algorithms or whatever it is. Of course, when you do the security assessment, you need to do investment analysis. So this is kind of doing in a more pragmatic way. This is the other. So you understand your system, you understand your adversary, be pragmatic or mission-oriented. That's what it is. The attack tree is kind of a central theme, like even NERC kind of uses attack tree as a semi-formal model. It is essentially and or kind of Boolean expression. So let's say here you have a OR AND gate. So there is an event here. These two events, because of this AND gate, that is one G4 and G5 is one scenario. That means there is a mission goal that is compromised. That mission goal can be compromised by compromising G4 and G5. G4 and G5, two events. If those two are compromised, or two elements, if those two are compromised, that mission goal can be compromised because this whole thing is valid. Or by compromising G2, the mission goal can be compromised. The third scenario is G6, because this is the OR gate. So G6 alone causes the mission to be compromised. The final one is G8 and G9, because this is AND gate, then also the mission can be compromised. So you have a tree like this. You can go and enumerate all those intrusion scenarios that can cause that mission. Mission means this root node is the mission that is compromised. What are the ways you can compromise? So you kind of list out, enumerate all those things, put it in this kind of tree structure. Then if you know what is the probability of this happening, what is the probability of this happening, then you can compute these kind of path probabilities. Each one is a path or scenario. You can compute this path probability. This is kind of intuitive. Why? Because fault trees are widely used in industry for analyzing fault and modeling. And tree structure is very simple and intuitive structure. There are fault tree solvers are there. It is used in electric power industry, avionics industry. So it is extension of that fault tree model to attack tree notion. Then you add defense capability there. It becomes attack and defense trees. If you have this defense capability, how the attack probabilities reduce, those kind of extensions are also there. So from NERC point of view, there is a document there, a few years old. They kind of try to define attack tree for the whole grid. Blackout happening in a major region, that is the mission goal from your adversary perspective. What are the ways by which they can achieve that mission? At a highest level, there has to be impact on the situational awareness, and also impact, there has to be some kind of instability in the physical system. Both has to happen simultaneously, because this is the AND property, AND gate. That means anything that is input to the AND gate, both must happen. Simply saying, oh, there is an information blackout, there is no change in the grid, grid is, let us say, stable state, then there is no impact, no blackout. You may not see the information, doesn't matter, it doesn't affect the system operation, things may be fine. But the problem is, the system is not stable. There are constantly making things, or generation comes up, going down, line going down, and so on. So there has to be a bulk power system instability coupled with information blackout or information loss. That is what will cause blackout in one or more region, not either one of them. That's why this AND gate comes in. How situational awareness itself can be lost. That is essentially the cyber. You collect information from field, wide area monitoring, and so on. One is the disruption on the communication network, the wide area communication network, or the energy management system or generation management system failure in the EMS, or the control center itself is basically compromised. So if either one of them happens, because this is the OR gate, if either one of them happens, there is an information blackout possible. On the other hand, when you look at the bulk power system, when the instability happens, either there is a major loss of generation, major loss of load, or major transmission outage. If any one of them happens, then there is instability in the bulk power system. So these three part of the R group, similarly the bottom three part of the R group. So you basically enumerate a scenario. One scenario could be, yes, there is a disruption in the communication network, and there is a line outage that happened. That is one scenario. Or other scenario could be the EMS failed and there is a loss of load, huge loss of load. That will lead to this and on the top. So one can go and mix and match all those different scenarios. Those are the scenarios. So this is at the top level. One can take it further to much more fine-grained level to utility control center, further down to substation and so on. Of course, this is at the top level at the like MISO and regional level. That is what the definition. So as I understand, NERC has developed that kind of attack tree model so that conceptually at least understand what are the things that can cause the bulk power system blackout. How do we go about mitigating them? Not in a mathematical way, but a more conceptual way that is already in place and being utilized. So they also use attack tree model as central to their threat and vulnerability assessment process. This is the CATF framework, risk management framework they use. Evaluate classified intelligence, sanitize for industry, like energy, ISAC, Information Sharing and Analysis Center. EISAC is the one sort of gathers intelligence, works with federal agencies, sanitize the information, send it to industry stakeholders, issue NERC alert, evaluate their NERC compliance to deal with those kind of things, work with other agencies to improve the SIP standards and other standards that are needed. This is the kind of thing they use, and I believe attack tree kind of provides a mathematical way of capturing all those things in that context as opposed to just purely a process-oriented approach. Just to summarize what we have discussed so far, in Module 2, we focus more on overall life cycle approach for cybersecurity, from deterrence, prevention, detection, mitigation, resiliency, and attack attribution. Then I also talked about how we can define risk assessment. What is risk? What are the challenges in computing cyber risk assessment, because the threat source is unknowable, but precisely not quantifiable. So we talked about the risk management process to begin with. Then I discussed the qualitative risk assessment, which is practically useful, widely used in industry. The quantitative risk assessment relies on a lot of data and assumption, more mathematical in nature, still in research stage, but there are synergy between quantitative and qualitative risk assessment. Those kind of explorations also happen. Then we kind of talked about risk mitigation. A lot of solution I talked about, they are all equally applicable, but in particular I focused on the pragmatic approach, mission-oriented thing that relies on the attack trees, and also how attack tree is used within NERC framework. Those are the two things I talked about. So with that, I stop here. Let us take maybe 5 minutes. Any question? We'll take few questions if you have online or participants who are here. After that, maybe we can take 5-10 minutes break. Yeah. Anybody question on the topics we have covered? Yes, please. More question is better, especially for our online students. I mean, students or engineers, whoever it is, professionals. It's beneficial.
I had a question about the mission critical tree that you showed.
Yes.
So the problem is that most of these systems in software world, it's possible to do attacks, right? I mean, you can give a copy of the software to somebody, and they basically take a copy and keep trying various attacks to see what causes what to fail. But in a system, often you have just one copy of the system, and you can't try attacks on that. So how do we even come up with a decision with the tree to determine what
great.
is?
That's a great point. In fact, we'll be focusing that in the fourth module, the test beds. That's why a lot of big companies, they have their own test environment. So one is production environment, even in software industry. Test environment is where they build and test. Then once they validate, they actually go into the production environment, or call it operational environment. So a lot of industries, I'm not sure whether MISO has it. Southern California Edison, for example, they have their own test bed. They have a miniaturized version of all those automation software, substation, control center, RTDS, racks of RTDS simulators. They're all coupled together as a hardware in the loop environment, within which they inject different attacks, poke different aspect of the system, and see what consequence. Everything what I described can be performed on a testbed environment. Of course, building that testbed costs money and costs human resource also. That is better than no doing anything on the operational environment. Yeah. So that is a lot of big industries do have, and I must tell you, we also have a testbed at Iowa State. Precisely, we try to do these kind of things. But the problem is the scalability, how big your system is, how realistic it is compared to the real world. So there are some issues that needs to be addressed, but that is the way to go. And most of the industries, they test it, even like individual components. You want to test a component or protocol, like Idaho National Laboratory, they have a test facility. They invite vendors, all the products come, they do testing and provide, not official certificate, but kind of provide report. These are things needs to be addressed. So that is more from a component, device, subsystem level. But what I'm talking about is industries do have a overall system in a simulated hardware in the loop sense, wherein they can do attack defense experiments for various scenarios. The point is you can essentially do the risk assessment using a test bed. Yes. Any other question? Let me ask you a question. MISO, do you have a response to that question? How do you do this kind of analysis? One is paper pencil, yeah, that's great. But beyond quality risk assessment, you need paper pencil. Somebody is knowledgeable, domain expert, based on their perspective, expertise, they fill out that. But if you want to do quantitative risk assessment, then you need to kind of do simulation or real experiments and vulnerability assessment, all those things. So that's where the test bed I said. But what is your experience from MISO perspective? I mean, in the interest of everyone, I thought the expert is here. It's appropriate to ask you.
I think it's a reasonable question to ask, but I'm in transmission planning. I'm not in the IT cybersecurity area. I know we have a test bed. I know we have a cybersecurity lab and stuff like that. So yes, we do some of those. I'm not privy to all that information.
Okay. And another important thing is, even doing patch management, your Windows operating system, patch update is happening, reboot. You can't do that. So the lab, cybersecurity lab or the test bed they do the patch update first, make sure everything is working for some period of time, observe, then they go into the production system. That's how it is done, yeah.
Manimaran, I have a question.
Please.
How is the analysis here and research different than other parts of the economy, like banks and stuff? They are also, I'm sure, very concerned about security, cybersecurity. Is there any overlap, or is it a very distinct area of research?
That's a great question. I mean, a lot of conceptual things like risk assessment, those processes. Process-wise, they are same. You can use the same process. Even this one, pragmatic approach. Who is your adversary? What is your system? But when you get into the details, what would be your consequences? What is the entry point? Where exactly your topology, how it looks like? A banking system looks a certain way. Whereas here, okay, you have transmission, generation, distribution, this is the way the SCADA network is, the network architecture will be different. So the differences will be in the detail, the technology level, that will call for different analytical tools and things like that. Whereas from the process level, risk assessment process, they are equally applicable to broader critical infrastructure, including banking, actually. Like a consequence analysis, right? When you say you create things, something will lead to something else, it's inherently a dynamical system, right? Whereas in some other system, it may not be that case. So each of those specific things, what is vulnerability here? Of course, the adversary sources could be the same. Different adversaries may be coming also. But the actual technology used and the cyber physical coupling, all those things will influence your actual consequence. Also, the type of model you use, detailed model for analysis, will be different. Yes. Any other thoughts? Doesn't need to be a question.
Related to what Professor just said, I was just thinking that a few days back there was a software upgrade at the bank that I use, and they said we are going to just shut down online access from midnight to 4 a.m. So they have 4 hours in which they can just shut down the whole thing and do whatever they want, and they are secure because there's no way anyone can get in. But how does the power system do that? What is
can you do that in power system? It is 24/7, right?
Yeah. So how does the high-level process that you said deal with?
Mostly that is the test bed. The test system, they do those testing. Then they have when they have maintenance or upgrade of some line, even physical upgrade, right? Then they will kind of switch to another line, and that's how while this upgrade happens. If those maintenance and upgrades are not done well, that will lead to blackout. That's what happened in India, the largest blackout in history. During a maintenance, one of those ultra high voltage line, there was some miscommunication that will lead to overload in other lines, the cascading. There were other phenomena too, but it was related to maintenance as well. Yeah. Okay. So shall we take 5 minutes? Okay. Thank you. We will be back in 5 minutes.